Good afternoon. Today I'm going to introduce the Fast Multipole Method using the language of matrix. We know that the Fast Multipole Method is used to accelerate the matrix vector product. So it is fitting and proper to introduce this method using matrix operations. Since the basic ideas can all be condensed in the 1D version of the Fast Multipole Method, so we are going to deal with the one-dimensional FMM. As Nico introduced in the last talk, the Fast Multipole Method aims to compute the matrix vector product where the matrix is determined by a kernel function, kappa here, where kappa is a function of two variables. In our case, we are dealing with the one-dimensional version, so the points x and y are all on the real line. And we are going to compute the matrix vector product KQ efficiently in linear complexity. Before we start, let's review Nico's talk last time. Actually, almost all the ideas in Fast Multipole Method were covered in Nico's talk. For example, problem formulation, low-rank approximation, and the concept of well-separated and nested partition and interaction list, although not explicitly stated, but she drew a picture about to explain the interaction list. There's one crucial concept that was not covered in Nico's talk, which is translation relation. And it is the relation that leads to a linear complexity algorithm. Without this translation relation, we can only get an algorithm with complexity of order n times log n, which was introduced in Nico's talk. We know that when we compute matrix vector product, the direct computation is quadratic, costs quadratic. And using tree code, we are able to improve the speed to n log n. And using FMM, we have linear complexity algorithm. The tools used in 2 and 3 is Taylor expansion. And what does Taylor expansion give us? It actually gives us a matrix factorization. Actually, it's an approximation to the original matrix K. And instead of computing the matrix vector product KQ, we are actually computing the matrix vector product of K hat and Q. By doing this, we are able to compute the matrix vector product efficiently with a linear complexity using FMM. First, we introduced the notion of well-separatedness, which was covered in Nico's talk, actually. On a real line, we have two sets of points, capital X and capital Y. we see that these two sets of points are well separated if this equation is satisfied. This means that there is a gap between the two sets of clusters actually, and the size of the gap, the size of the distance between the two clusters is comparable to the size of each cluster. For example, if the first sets of points are in 0, 1, and the second sets of points are in 2, 3, then these two sets can be considered well separate. And the interaction between well separated sets is called far-field interaction. If we have two well separated sets, then we show that we can approximate the kernel function accurately using Taylor expansion. We choose the center of each cluster, where A is the center of cluster X and B is the center of Y. And we do this manipulation to produce a function in the form 1 over 1 minus t, where t here by the definition of well separateness, t is less than 0.6. And using Taylor expansion for 1 over 1 minus t, we can produce this series expansion with an error epsilon r. And actually this expansion can be written in a matrix form like this. The benefit of this expansion is that we separate the points x and y in the sense that we write the original kernel function as a sum of functions which are a product of in the form of fx times fy, as you can see here, so that we have this factorization where C is a coefficient matrix. We see that the error term in the Taylor expansion is comparable to tau to rth power, where tau denotes the separation ratio, which is 0.6 in our setting. In previous slides, we showed how to factorize a single term kxy, and if we have many points x1 to xn and y1 to yn, we can actually factorize the original kernel matrix in the form of UB times V transpose.
Can you say something about why we want to do that? Why it's beneficial over the other form?
Notice that the size of the original matrix is n by n. And this factorization gives us much smaller matrix where the size of U is n by r. And the size of C is r by r. And the size of V is also n by r, where r denotes the number of terms in the Taylor expansion. And usually r is extremely much smaller than the size of than n. So by factorizing K into the form UBV transpose, where the matrices have smaller sides, we can compute the matrix vector product efficiently, because R here is really small in the sense that R is roughly equal to the log of epsilon, where the epsilon is the prescribed accuracy. So we can see that R is independent of the size of the problem. If we set the accuracy to 10 to negative, for example, negative 10, then we see that R is roughly 10 or 20. Usually n is quite small, maybe 1,000, 1 million. We see that if two sets of points are well separated in the sense given before, then we can factorize K into U times B times V transpose with an error term. Instead of computing KQ directly, we compute K hat times Q, namely U times B times V transpose times Q, where the cost for V transpose times Q is R times N, and so is U times a vector, and we sum it up to have a linear complexity algorithm. It should be pointed out that equation 1 here is one of the two essential building blocks of fast multipole method. Why not give it a name? So we call it BBS1, building blocks 1. So far, we conclude that if two sets of points are well separated, then we can have a linear complexity algorithm using the factorization here. But in general, points are not well separated. Usually they are distributed in a same interval, for example, 0, 1. In this case, we are going to use the results before, namely, we partition the interval into equal parts, and we seek far-field interaction there, where we can use the matrix, where we can use the factorization introduced before, which provides efficiency in computing the matrix vector product. Now we partition the interval according to this perfect binary tree. In the second level, we partition the interval into two equal parts corresponding to the second level of this tree. Namely, we partition the interval into I7 and I14 corresponding to the nodes in the second level. And in level 3, we further partition each subintervals into two equal parts to get 4 subintervals corresponding to 4 nodes in the binary tree. And inductively we partition the intervals, subintervals. Then when do we stop partitioning? The number of levels in this tree, which we denote by capital L, is determined by the size the size of the problem. We are going to reach a level capital L so that the number of points in each subinterval corresponding to the leaf nodes is order R, which means that the number of points in each subintervals at leaf level is roughly a constant. And it can be seen that capital L is roughly log of n, which is also small. We know how to compute the far-field interaction. What if two sets of points are next to each other? For example, two neighboring subintervals at leaf level. How do we compute it? Here is the definition of near-field interaction and correspondingly the near neighbors. Well, as I mentioned before, that we are going to use the factorization for well-separated clusters in the general setting. But how can we determine which pairwise interactions do we consider in each level? You know, there are many intervals, many levels. How to compute the interactions in a systematically way? Here we introduce interaction list. The interaction list is defined for each node in the binary tree. For node I, the interaction list consists of nodes that are well separated from I, and whose parents are near neighbors of the parent of I. Since the nodes in Li are well separated from I, we can use the factorization before to compute the interactions between them. Here is some examples of interaction list. For node 3, by definition before, the potential nodes for L3 are well separated from 3, which are 10 and 13. But another requirement is that their parents must be near neighbors. And we see that the parent of 3, which is 7, is indeed the near neighbor of the parent of these two nodes, which is 14. What about the interaction list for node 11? The potential nodes for the interaction list of 11 are 1, 2, 4, 5, 8, which are well separated from 11. But the parents of the node, this node, must be near neighbor of the parent of 11, which is 13. So the only option left here is node 8. At level 3, where there are 4 subintervals, we know that, of course, we can see there are well-separated clusters. For example, the first subinterval and the third or the fourth subinterval. So we are able to compute the factorization corresponding to the interaction between those two clusters using BBS1. This figure this figure shows the interactions corresponding to level 3, where the blue blocks are what we consider here, namely the blue blocks corresponding to far-field interactions at this level. For example, the interaction between 3 and 10 is far-field, which corresponding to this block, 3 and 10, and 3. And the interaction between 6 and 13 corresponds to this block, this blue block. We know that for each of these blue block, we can use low-rank factorization introduced before in the form of UBV transpose. So at this level, this matrix can be factorized where the white block denotes the zeros. And here is the factorization of this matrix. Why we can factorize the matrix like this is because the basis, the column basis for each row block, for example, for row block 3, only depends on node 3. It is independent of the columns. So the column basis for this row block is just U3 here. And the block we factorized before is here, U3, B310, and V10 transpose. If we compute the matrix vector product for this matrix, it immediately follows that the complexity is linear. Similarly, we go to level 4 to find well-separated clusters or far-field interactions. As I mentioned before, this kind of interactions can be found using interaction list. For each node I in this level, we pick up nodes in interaction list Li, and then we factorize the corresponding blocks using BBS1. For example, the green blocks here, say this block, denotes the interaction list. The interaction between a node I and a node J, where J is in the interaction list of node I. Say for node 5, the node 9 is in the interaction list of 5. And the block corresponding to the interaction between 5 and 9 can be factorized in this form. Similarly, we can factorize all other blocks colored green. And the column basis for each block row I, only depends on I. Here for block row 5, the column basis depends on node 5. Only depends on node 5. And this gives us a factorization of the whole matrix here. Similarly, the complexity for computing K4 times Q is linear. inductively, we can find far-field interactions at each level and factorize the corresponding matrix into the form like this, where the complexity for computing matrix vector product is linear. We stop at the leaf level of the binary tree, where the remaining interactions are all near-field interactions. Notice that in the leaf level, as I mentioned before, the number of points in each subinterval is of order R. So the matrix corresponding to the near-field interactions at leaf level is a banded matrix where the width of the band is of order R because the number of points in each small subinterval is of order R. And to compute the matrix vector product of this banded matrix, we know that the complexity is obviously linear. Here are some terms we are going to use in later slides. We factorize each matrix at level L into this form, where UL is called column basis at level L, and VL transpose is called row basis at level L. Where, as we see, that the column basis or row basis are all diagonal, block diagonal matrices. What we have done so far can be illustrated using this figure. At level 3, we consider interactions corresponding to I and J, where J is in interaction list of I. And in next level, we do the same thing. So the whole matrix is decomposed hierarchically into a bunch of matrices, where for each matrices we have a factorization with corresponding matrix vector product complexity linear. Here N is a banded matrix left over here, banded matrix. We know that for each KL, the complexity to compute KL times Q is linear. So this decomposition gives us an algorithm to compute matrix vector product where the complexity is roughly L times N. Here, L is the number of levels of the binary tree, and the level and the capital L is of order log n. So this decomposition gives us the n times log n algorithm, which is actually the algorithm that Nico introduced in last talk. Now we sit down and think about what kind of trick leads to the n log n algorithm. We see that the only tool we use is the Taylor expansion and the corresponding matrix factorization, BBS1, for well-separated clusters. How to proceed to kill the log n term in the complexity? We know that for each component KL has a factorization in the form of UBVT. And it can be seen that KL and KL plus 1 are actually related. Here comes the translation relation. For a parent node P in the binary tree with corresponding where C is a child of P. AP corresponds to the center of the subinterval IP, of the subinterval corresponding to node P, and AC denotes the center of the subinterval corresponding to node C. We do this algebraic operation to express the function corresponding to P as the one corresponding to C times a constant. Write this formula into a matrix form. We have this relation where T depends only on the two centers, AC and AP. And this equation is another one of the two building blocks of FMM, which we call BBS2. Here is an illustration of this factorization. Recall that the function f appears in the definition of matrix U here in matrix U. And UP depends only on the center of the subinterval P, and similarly for UCI. The translation relation gives us a factorization of the column basis UP. And by this factorization, we see that we can obtain the information about a parent node P using the information about its children, C1 and C2. If we put this into the factorization of the large matrix we introduced before, we see that the column basis at level L-1 can be obtained from the column basis at level L, one level below level L-1. This exposes the relation between between the matrix KL minus 1 and the matrix KL. Since we know that for each matrix KL, there is a factorization like this, and we know from the previous slide that the column bases UL are nested, and so is the row basis VL transpose. So by writing the column basis UL, by extract the information at leaf level and then pass the information to level L, we have a factorization of UL. That is, we use the translation relation, we use this relation recursively until we reach leaf level, which is level L. So here U3 can be written as a product of U capital L, U T capital L minus 1, T capital L minus 2 until T3, which leads to the factorization here. By incorporate this factorization into the decomposition for the original kernel matrix, we see that the kernel matrix K can be written in this form, which we usually call telescoping expansion. Matrix U capital L is the column basis for leaf level, and matrices T are translation matrices. What benefit can we get from this decomposition? We see that this decomposition gives us a linear complexity algorithm. For each matrix TL, to compute TL times a vector Q, the complexity is a constant times 2 to lth power. So to compute all such matrix vector products, we have this sum, which gives us a linear complexity. And similarly, to compute BL times Q, the total cost is also linear. And so it remains to compute the matrix vector product of N and the column and row basis. And we know that N is a banded matrix, and the column basis or row basis is a block diagonal matrices, where the size of the column size of each diagonal block is R, which can be viewed as a constant. So the matrix vector product for these matrices is linear. Then we see that the total cost for computing the matrix vector product of K is linear. let's recall what gives us a linear algorithm from the n log n algorithm. Besides the factorization BBS1 in the n times log n algorithm, we have an extra BBS2, namely the translation relation. By taking advantage of the translation relation, we found the relation between column bases between adjacent levels, which leads to a telescoping expansion of the original matrix K. So this is an illustration of the partition we did before, where different colors correspond to different levels. As, for example, the blue block corresponds to level 3, and the green one corresponds to level 4, and so on and so forth. So the next time when we see this kind of pattern, we know that with high probability, this has something to do with fast multiple method. Thank you.